Right, so this is part 2 of the honors final exam review. Okay, so the first question is another periodic trend, electronegativity again. And again, as a reminder, on the periodic table, if we take away the noble gases here, which don't have measurable electronegativity, then the king of electronegativity is fluorine in the top right, and the trend is that it increases moving up and to the right. So the bottom left would be the smallest electronegativity. So to put these in order of electronegativity going up, you first of all need to know, or would know, that it's got to end with fluorine, if that's one of the choices. And then that leaves us with these two choices. Sodium and magnesium are on this side of the periodic table. They're metal elements. And then nitrogen and oxygen are over here. This is sodium, magnesium. Okay, so these over here are going to have very low electronegativity. These are very close to fluorine, so they're going to have high electronegativity, and they go in order from left to right in this answer choice. Which of these elements is most likely to form an ionic compound? Ionic compounds are formed when a metal bonds with a non-metal. Okay, so you've got one element from the left-hand side of the periodic table, metals. Non-metals are in the upper right, so you've got one metal, one non-metal. Those are generally going to form ionic compounds. So the first one is two metals, sodium and aluminum. The second one is two nonmetals. The last one is two nonmetals. The only one that's a metal with a nonmetal is magnesium and fluorine. So that would be the ionic compound MgF2, magnesium fluoride. Which of these molecules is non-polar? Well, if you should always remember, first of all, that water is very polar. Okay, you're looking for things that are symmetrical. When you want non-polar, symmetrical is the way to go. If you do out these Lewis diagrams, right, nitrogen is going to end up something like this with 3 fluorines, so that's not symmetrical. Bromine trifluoride is going to end up looking something like this. So this one does appear to be symmetrical. And then if you did out the other two, the carbon with the 3 hydrogens and the bromine, well, that's not symmetrical because you get the one bromine over here, so that's not it. And then the SO2, you might think, well, that could be OOS, and that would be symmetrical. But when you do the Lewis structure, you find out that it's got the 2 lone pairs, which means the shape is actually a little bit bent, similar a little bit to a water molecule. So it's not symmetrical because the oxygens are at the bottom, the sulfur's at the top. So the only one that's symmetrical and therefore nonpolar is the bromine trifluoride. Which of these species are isoelectronic? Okay, which pair are isoelectronic? So isoelectronic, the term just means they have the same electron configuration. And so for any two elements to have the same electron configuration, one has to be a neutral atom, one has to be an ion. So that's the first thing. So we can eliminate these two because they're two different elements, neither one is an ion. These are two different elements with the same charge, so they can't have the same electron configuration, because even though, sulfur and selenium, they are both -2 ions, so the outer shell looks the same, but they're on different energy levels, so those aren't the same. So krypton and bromine with a -1 charge, krypton is going to have a configuration that ends with 4p6. This is krypton. And then bromine normally has a configuration that ends with 4p5. However, since this is bromine with a -1 charge, that means it's got one extra electron. We add that on, we get 4p6. So these two atoms are isoelectronic because they share the same electron configuration. Right? P3 and neutral chlorine are not the same. Hydrogen ion and helium are not the same. Krypton and bromine with a -1 charge, or bromide is actually what we would call that ion, are the same. So we had a second question on this page. BF3 is a well-known molecule. This is, I guess, just horrible grammar because there really isn't a question here, but the question is basically which of the following statements applies to BF3. And as we just saw in the question about polar molecules or nonpolar molecules, bromine trifluoride, which would look something like this, is a trigonal planar molecule with a central atom of boron, not bromine, boron. And if you look, this boron atom only has 6 electrons connected to it, which means it is an exception to the octet rule that says all atoms want 8 valence electrons. Boron is an atom that can be satisfied with only 6 because of its electron configuration. So that's an exception to the octet rule. What is the electron geometry of ammonia, NH3? Well, if we do out the Lewis structure, we've got this nitrogen, we've got 3 hydrogens, we have a lone pair up here. Okay, and when you look at the central atom, which is the nitrogen, it has a total of 4 electron regions, or regions of electron density, or bond areas. There's lots of different terms for it, but it's got 4 electron regions. It has 1 lone pair and 3 bonds, bond pairs. So the configuration that has 1 lone pair and 3 bond pairs is called trigonal pyramidal. Which of the following has bond angles slightly less than 120? Well, let's take a look at the Lewis structures, and then we will figure out which one is going to have a less than 120 bond angle. Okay, through the magic of television, here are the Lewis structures for these 5 polyatomic ions. And what we're looking for here is slightly less than 120 degrees, which means pretty close to a trigonal planar shape. So the triangle would have bond angles roughly 120 degrees. We're looking for something that's close to that, but not quite. So the first one that I'm going to eliminate is this one over here, because this is 2 atoms. 2 atoms can only have one shape, and that is linear. So it's not the NO minus. This one, the carbon with the 3 sulfurs around it, has exactly 3 bond regions. Okay, that's going to give you a trigonal shape. No lone pairs. So it is actually going to be trigonal planar, which means it's going to be exactly 120 degrees. Then these 2 are both bent shapes because they have 2 bonds and then 2 lone pairs up at the top. So these are both similar to water molecules. So they have 4 bond, or 4 electron regions rather, 2 bonds, 2 lone pairs each. So that actually gives them bond angles closer to 109, which is, yeah, you could say slightly less than 120. But if we look at this last one over here, we have 2 bond regions, 1 lone pair, so 3 electron regions, which would give you a trigonal shape similar to this one, except because of the lone pair at the top, the other two bonds get pushed down slightly. So it goes from perfect 120-degree bond angles to something a little less because of the lone pair electrons at the top. So this is the answer we're looking for. When you have a pan of liquid water and ice, and you put it over a flame on the stove and stir it vigorously, which of the following would be correct? The temperature starts to rise immediately. The temperature rises slowly at first, and then more and more rapidly. The temperature rises immediately. The temperature rises, but only after the ice melts. Well, what you need to bear in mind here is that when you have things that are going through phase changes, the energy diagram would look something like this. Okay, let's say you had solid ice, pure ice, and you started to warm it up. Well, it would warm up, it would warm up, it would warm up, it would warm up until you hit 0 degrees. That is, in this case, the melting point, because we're going up instead of down. Going down would be the freezing point. Once you hit 0, the temperature levels off. Okay, this is the temperature is over here on this axis as we're doing it. So the temperature increases in the solid state until you reach the melting point. Once you reach the melting point, the temperature levels off because all of the energy going into the ice is going into melting the ice. So the temperature cannot go up until all the ice is melted, and once all the ice is melted, then if you keep heating it, the temperature will go up again until you reach the boiling point up here somewhere, 100 degrees Celsius, and then it will level off again while all the water boils. Once all the water boils, you can heat the steam up even further. So we get this sort of stair effect in the temperature when you're heating up any substance, but in this case we're talking about water. So the answer here is the temperature will only rise once all the ice is melted. If you start with ice water, so basically you take some ice, you let some of it melt, and then you start to heat it up. If you take the temperature of that water, it's at 0 degrees when you start, and it will stay at 0 degrees until all the ice is melted, and then it will go up again and make its way up to 100 degrees eventually. So another sort of state of matter or phase question, and in which phase or state are the particles close together but free to move around, so they're not locked in place? Well, that would be liquid. Right? Liquid are closely packed particles but not locked in particles. They're able to move around each other, which is what gives a liquid the ability to flow and change its shape. Gases are not close together, but they are able to freely move around. Solid particles are close together, but they are not free to move around. And plasma are super high energy particles, and we haven't even really talked about plasma. Okay, if a chemist needs 225 milliliters of a 2.4 molar hydrochloric acid solution, what stock solution, how much stock solution, which is 12 molar when we get it from the manufacturer, must he add with water to form this solution? So we're going to take the concentrated stuff, add some water to it, and get it to the amount we want. Well, this is using what's called the dilution equation, which says that the starting molarity times the starting volume is equal to the final molarity times the final volume. And the way this typically works when we're making these solutions is we know, it's kind of backwards, we know what we want the final molarity and the final volume to be. So we put that in. The final molarity we want is 2.4 molar, and we want to have a volume of 225 milliliters of it. So we know what we want. We just need to know how to get there. In these problems, when you're doing dilutions, it doesn't matter whether it's in liters or milliliters as long as it's consistent from left to right. So the molarity is 12 in the concentrated solution. The question is, how much of that concentrated solution must we start with in order to have a 2.4 molar solution when we dilute it to 225 mils? And so the question here is, what do we get when we now divide both sides by 12? And when you do that out, you find that V1 is equal to 45 milliliters. So we would take the stock solution, we'd measure out 45 milliliters of it, add that into a flask or beaker, graduated cylinder, or volumetric flask, and then we would add water until the total volume equaled 225, and at that point the concentration would be 2.4 molar. So 45 milliliters is what we get there. So here's a question about mole fractions, and this one actually asks you to do a little bit of ideal gas law as well. So what we're going to use here is the ideal gas law because we need the number of moles of each. So PV equals RT, or sorry, over RT equals N. And we're going to do that for both of them. The pressure is 15 atmospheres for the oxygen. The volume was given as 4 liters for the container. The ideal gas constant and the temperature are going to be the same for both of these things that we're calculating, so we're actually going to be able to eliminate those because they're not really variables, they're not going to change. So what we really have is, that's for the oxygen, 15 times 4. So what we're left with is the O2 is going to be equal to 15 times 4, and then the N2 is going to be 7 times 4. So when we put that into the mole fraction equation, the mole fraction says that, the moles of A divided by the moles of A plus moles of B. Okay, so basically the moles of whatever you're targeting divided by the total number of moles in the mixture. So since we're talking about the oxygen, that's 15 times 4, and then that's divided by 15 times 4 plus 7 times 4. Right, and we do all that out, we get 60 over 88. We divide that, and we get 0.68 would be the mole fraction. What is the molality of a solution prepared from 0.585 grams of sodium chloride with 100 grams of water? So the molality, little m, is moles of solute divided by kilograms of solvent. Okay, so the moles of solute, the moles of sodium chloride, is given by dividing the 0.585 grams by the molar mass of sodium chloride, which is 58.4, which gives us something very, very close to 1/100th. And then we take that and we divide that by the kilograms. Well, we have 100 grams of water, which is 0.1 kilograms. So 0.01 divided by 0.1 is 0.1. So it is a 0.10 molal solution. Okay, which of the following is not a colligative property? Remember, colligative property means it is a physical property that is affected by the number of solute particles in solution. And all of these would be affected by that, except the molality. Right? The molality is affected by the moles and the kilograms, which is not the same as saying the particles, because all the other things, osmotic pressure, vapor pressure lowering, freezing point depression, etc., boiling point elevation, those are dependent on the number of particles, not the nature of the particles. Molality can be affected by the nature of the particles because we're talking about molar mass, etc. Okay, which of the following aqueous solutions would have the lowest freezing point and the highest boiling point? What we're really looking for here is which would have what's called the highest Van't Hoff factor, or I value. The I value is the number of particles essentially in the solution, or the multiplication factor of the particles in the solution. So 2 moles of potassium chloride, or 2 molal. Potassium chloride is going to have an I factor of 2. Sodium chloride, or sodium phosphate rather, okay, 1.0 molal sodium phosphate, it's going to have an I factor of 4. Sodium chloride has an I factor of 1. Calcium chloride has an I factor of 3. So it's CaCl2. And then aluminum 3 nitrate. That's going to be aluminum 2, nitrate, NO3, 3. Didn't need the parentheses around the aluminum. That, and that's a 1.5, that is going to have an I factor of 5. 2 aluminums and 3 nitrates. So even when you factor in or take account of the fact that we've got a 1.5 molar, so 1.5 times 3 would be 4.5, 2 times 2 would be 4, this is 4, this is 1. Even with the extra concentration, and this is a 1.5 molal aluminum nitrate, so it would actually be 7.5. And this is just a relative number relative to the others. Right? The biggest I value and the molality doesn't change that. You know, if this was 4 molar, or 4 molal KCl, you might have a different story. But the one that's going to have the highest boiling point and lowest freezing point is the aluminum nitrate solution. Colligative properties depend on which of the following: the identity of the solvent and concentration of the solution, identity of the solute and concentration of the solution, only on the identity of the solvent, only on the identity of the solute, or only on the concentration. Well, it does not ever depend on the identity of the solute. That's one of the key factors of colligative properties. Doesn't matter what it is. All that matters from the solute point of view is how much there is. So it does matter the concentration, but the identity of the solvent is also a factor. That's why when we do the calculations, like the change in freezing point, we have I, right, which takes into account the concentration. The molality takes into account the concentration. Then we have this constant, right, the freezing point constant or boiling point constant, and that varies with the solvent identity. So it depends what the solvent is, whether it's water or ethanol or benzene or whatever, and it depends on the concentration of the solute. Talking about the relationship between gases and pressure, temperature and pressure, and the solubility of gases. Gases in general, when it comes to solubility in water in particular, have the opposite effects of most other solutes in water, and gases generally have a decreasing, we're to pressure first. Pressure, if you increase the pressure, you increase the solubility of the gas, because you sort of are pressing the gas into the solution and holding it there. That's why sodas and things like that are packaged under pressure, because it holds the carbonation in. If you increase the temperature, you decrease the solubility, because the gas is able to escape more readily at higher temperature because the particles have a lot more energy. So the correct answer choice here is increases with pressure and decreases with temperature. What would be the correct steps in order to determine the heat of solution of NaOH? Given these choices, the first thing we're going to do is add water to the beaker. Right, we got to put some water in a beaker because we're going to measure the change in temperature of that water. So that means that C has to be the first step, which would eliminate these two choices. And then the next thing I'd want to do would be, since we're talking about the change in temperature, we're going to have to read the original temperature of the water before we do anything to it, which happens to eliminate this choice because A is going to be the second step. But if you follow it through, you pour the beaker, you take the temperature of the water before you do anything, then you add the sodium hydroxide, give it a stir, wait for it, and then watch the temperature as it changes. and then take the final temperature reading. That would be the correct order to do that in. If there was any mass involved here, you'd want to mass the water before you did anything. You'd want to mass the sodium hydroxide before you did anything to either one of those two things. So just if there's a question like this, really think through, in what order do you need to have the data in order to have the numbers you need for your calculations at the end. Are you massing things before and after you add stuff? Are you taking account for things like the mass of empty beakers and that sort of thing? Okay, if we're trying to calculate the heat of fusion of ice in a coffee cup calorimeter, we've taken the mass of the cup and the contents, we've added ice and watched the temperature change while the ice melts, and then we wait a certain amount of time and take the temperature change, calculate the amount of energy that was exchanged, and then based on the mass of ice that was melted, we did something similar to this. We calculate how much energy was given off as the ice melted, or absorbed by the ice as it melted. So the question is, if the student, say, instead of waiting for all the ice to melt, they just waited a certain amount of time and then removed the ice, and then took the final weight and calculated the temperature based on that, what would happen to their calculations if, when they remove the unmelted ice, which in the first place is not a great idea, better to just let it go. If they remove the ice, they also removed a significant amount of water. What would the effect be on their calculations? So the effect here would actually end up being that you would think that the heat of fusion of ice is bigger than it really is. Because when you take the ice out and then you take the mass, and you're assuming that the difference between what you started with and what you ended up with is the melted ice, well, you're really measuring the amount of water in the cup. And if you took out a little bit of extra water, then you're basing the heat of fusion on a smaller amount of ice, smaller amount of water. So you're going to assign the amount of energy to an amount of ice that's too small, which means you're going to think that it took more energy than it did to melt that ice. So again, just like with the previous question, we're talking about experimental design kind of questions. You have to think through how will an error that's made affect the calculations. Is it going to be too big, too little? Does it not matter? And then, if when all else fails, if you do sort of make up some numbers and put them in and see what happens, that's sometimes a very effective way to do this if you're stumped. Just make up some numbers and plug them into a calculation and see what happens if you change one to be too big or too small. How does that affect your answer? So that's the end of Final Review Part 2.